Question 48 now. We've got some pretty expensive sounding badges that we're trying to help James with. He wants to use all of his braid, but he wants to minimize the area. Perhaps the material he's using for the actual badge itself is more expensive than the braid. Anyhow, let's see how you got on with this question. So here are the badge, or two badges, and in order to try to move forward with this, I better think of a couple of letters to describe the size of the badges. I think maybe R for radius and L for the length of the side. What do you think? Maybe that's a good starting point. So I can write down an equation now which is equivalent to the fact that we've got 12 centimeters of gold braid to go around the edges, and he wants to use all the braid. So the circumference of the circle plus the perimeter of the square must add up to 12. I can't really do anything with that, or I'm not quite sure yet what I want to do with it even. So I'll just park that there for a moment. Now we're trying to find the minimum area. So minimum implies some kind of differentiation at some point. So I better try and find something to differentiate. Let's find an expression for the area of the circle plus the area of the square. So there's the expression for the area. But I can't differentiate this as it stands because I've got two variables. The R and the L both depend on each other. So before I can differentiate, I need to eliminate one of those variables. So this is where the equation that I've written down here is going to come in handy. I'm going to make L the subject of that. And when I do that, I get this expression here. And then I can substitute that for L into this expression for the area. When I do that, this is the revised expression for the area, which has only one variable in it now, so that's good. Pi is not a variable, pi is just a number. So I need, before I can differentiate, I'll multiply the brackets out, which gives me this, and then I'm in a position that I can differentiate. So when I differentiate, I get this expression here. So I'm trying to find the minimal area, so I must make the dA dr equal to 0, and when I do that, I get R times this bracket must equal 3 pi, and from there, dividing by that big bracket, dividing 3 pi by that bracket here, gives me a value for R of 0.84 and a value for L exactly double, 1.68. So that says that the width of the circle and the width of the square have to be the same. Does that surprise you? It's quite an interesting result. I wonder if you can think why that might be. Anyhow, have we answered the question? Which together have minimal area? What dimensions should the badges be? And what will the minimal area be to use all the braid? We haven't worked out what the minimal area will be yet. But when you put the unrounded values for R and L back into the expression for the area, you get the area equals 5.04 centimeters squared. So that's the area. Have we answered the question yet? Find what dimensions should the badges be? What is the minimal area using all the braid? We've got this final part of the question here. Prove that the area is minimal. So how do we do that? Well, there's more than one way of doing that. The way I'm going to do it is to use the second derivative. I'm differentiating this a second time to get d2a dr squared. And when I do that, I get d2a dr squared is this expression here, which is simply a number, and it's a positive number, and that indicates that the area will be minimal. So how did you get on with that question? I hope you got the same answer. If you did, well done.